All right, good morning. How's it going? Don't all speak at once. All right, we'll do what we've done previously. I'm going to pass around some pads of paper. Please put your name and email address and any words of wisdom that you want to share. All right, so let's talk about a few things. Towards the end of the semester, things come up fast and furious. There's a quiz on Canvas. It's due before noon on Friday. Exam 3, Reflection and Planning. Also, Thursday, I'm out of the office all day, so my office hours are canceled. You should have received an email inviting you to complete end of semester evaluations for Brian, Melissa, and for myself. If you complete all three of those, you get 1 point added to the final exam, and it's the final exam and both the optional exam. It'll be added to that. I only know whether you've completed it or not. And actually, I can't really tell whether you've completed it. I know that you've submitted something, right? So the things are completely anonymous from our perspective. I personally, and I think Melissa and Brian, all want to know how well we're doing. So please, give us constructive feedback. The deadline for the survey is May 5th. I have nothing to do with the administration of it, so that date is fixed and firm, right? All right, so and then regarding the ACS standardized exam, the deadline is today at 3 p.m. to request an alternative time or some accommodations for that. So if you haven't got in touch with me, please do that today. And then some folks have asked about the ACS study guide. You can purchase them online. Alternatively, I have one over on reserve in the bookstore or in the library. All right. And then dates coming up next Thursday, that's May 2nd. Next Thursday will be the optional standardized exam. It's going to be in 1210 LeBaron, starting at 6:30. Review sessions for the final. There'll be one on Friday the 3rd. That starts at 2 o'clock, so it's right after the afternoon class. That's a new room, 1810 Gilman. And then Sunday, Melissa will facilitate one at 4 in 1104 Gilman. All right. The only other thing I wanted to just remind everybody is that for the optional ACS exam, you can't use your cheat sheet. All right. So from day-to-day experience on the exams that you don't use them as much as you'd think you'd use them, right? So this is letting you work without a net, and then the exam the following week, you've got your net. Okay. Make sense? All right, things we've talked about previously. We've looked at the slopes of the coexistence curve on phase diagrams. We saw specifically the solid-liquid slope of that coexistence curve tells us about the density of the solid versus the liquid. We've looked at a plot of the Gibbs energy as a function of pressure and the Gibbs energy as a function of temperature. We saw that the slope is equal to the volume for the first graph. It's equal to the negative of the entropy for the second graph. And the other thing that comes out of these graphs is that it emphasizes the idea that the phase that we expect to observe our substance in is going to correspond to the minimum Gibbs energy that's available at that temperature and pressure region. All right. We've also shown that substances move from high chemical to low chemical potential, and when we're at equilibrium, there's no driving force to move from one phase to the other, so chemical potential is minimized. The chemical potential is the same in all phases at equilibrium, and so that should make some sense. There's no driving force to move from one phase to the other if we are at equilibrium. We've shown that the chemical potential of a pure substance is the same as the molar Gibbs energy. We derived the Clapeyron and the Clausius-Clapeyron equation, both of which give us basically the coexistence curves on our phase diagrams. All right, so today what we're going to be doing is we're going to be finishing off our discussion of the Clausius-Clapeyron equation, and then from there we're going to start talking about liquid-liquid solutions. So we'll see why distillation works in the next few days. Along the way, we're going to introduce partial molar quantities. We've already introduced a partial molar quantity. That's the chemical potential, right? But we're going to take that information and generalize it a little bit. We're also going to introduce something called the Gibbs-Duhem equation. and talk about how we describe liquid-liquid solutions. Right? And what we're going to see is that we're going to have ideal solutions, and then we're going to have deviations from ideal solutions. Right? So this blank space is the stuff that I put on the board. So we've previously been talking about mole fraction in the gas phase. That's the number of moles of our component over the total number of moles. We indicate that mole fraction with a Y. Because we're dealing with solutions that are in liquid phase, also we have a different distinguishing character for that. We use X. So X sub I is the mole fraction in the liquid phase of a component over the total number of moles in the liquid phase. Also, we're going to introduce this asterisk. So this superscripted asterisk, when you see that, that says it's the pure component. Right? So this means I have a mixture that is so dilute, the only thing I've got is one component. Okay? All right, the other thing that we're going to do, your book doesn't do a very nice job of this, so I wanted to make sure we talk this through. We've previously shown that dG dP is the same as the change in the chemical potential due to the change in pressure. And for a long time, we've been saying dG dP is the same as the volume. All right? And now that I can say that the change in the chemical potential due to a change in pressure is the same as the volume, I can rearrange this and assume an ideal gas and integrate the dependence of the chemical potential on the pressure. Now, if you think about it, we've done that for the Gibbs energy. The result of that integration gives us the Gibbs energy at any temperature and pressure is given by the Gibbs energy at 1 bar at that temperature plus RT ln P. All right? All we're doing now is we're just extending that to chemical potential. So chemical potential at temperature and pressure is given by the substance's chemical potential at 1 bar plus RT ln P. Okay? Does that make sense? All right, so moving forward, we had just derived initially the Clausius-Clapeyron equation. Okay? All right, so what we've basically shown is that d ln P dt is the same as delta H over RT squared. So delta H of vaporization over RT squared. All right? And I can rearrange this and say d ln P is equal to delta H of vaporization over R times 1 over T squared dt. Okay? Now, if I'm interested in knowing the dependence of the natural log of the pressure on the temperature, that means I need to integrate it. Okay? So I'm going to integrate here, and I'm going to integrate. We know R is a constant. What we're going to assume is delta H is not strong function of temperature. So that means I'm going to be integrating 1 over T squared dt. Okay? All right, so we'll be going from T1 to T2, and this will be ln P at T1. No, ln P1, ln P2. Okay? All right, so before we do this integral with limits, I'm going to choose to do an indefinite integration. All right? So the indefinite integration of d ln P will be the natural log of P plus a constant. All right? So I can write ln P equals. Just keep in mind that we have a constant. Okay? And then on the right side of this, well, delta H and R are constants. So delta H of vaporization over R. And that means I need to take the integral of T to the minus 2. What's the integral of T to the minus 2? Not quite. There's a negative in there, so we'll take that from you. But T to the minus 2 integrates to T to the minus 1. Okay? So that's 1 over T, right? And then, of course, when I do that integral, I have a constant. So I have a constant and a constant. I lump them together and just say a combined constant plus C. Okay? So I wanted to take a moment to just look at this in terms of what functional form we expect. So this is Y, all right? If I choose 1 over T to be X, then what's my slope if I assume a linear behavior? Minus delta H over R, right? Plus that, right? And that's what we show in this graph. We've got the natural log of the pressure as a function of 1 over T times 1,000, okay? Right. And the slope of this line is the negative of delta H of vaporization over R, right? Is anybody taking Chem 322L right now? You did this experiment, right? So you go in and you measure boiling points as a function of pressure, right? That gets you the natural log of the equilibrium pressure as a function of temperature. And from that experiment, you can determine delta H of vaporization for that substance. All right, then in terms of a definite integral, all right, we can say that the left side, natural log of P2 over P1, is going to be given by minus delta H of vaporization over R, and then 1 over T2 minus 1 over T1. Right? And then I can do some algebraic manipulation to get these to be a single term, and that comes out to give us plus delta H vaporization over R times T2 minus T1 over T1 times T2, right? No additional information, it's just a different form, okay? All right, so we did this for the temperature dependence of vapor pressure. So that's the equilibrium between liquid and vapor, right? We can also do this for sublimation, works exactly the same way, okay? And if you think back to how we've derived this, we needed one phase to be in the gas phase, right? Because we used the ideal gas law. All right. So we know the vapor pressure of a liquid or solid are 2 or more temperatures. We can calculate delta H of the phase transition over that temperature range. All right, we're shifting into chapter 10, where we're going to talk about liquid solutions. All right? And we're going to start by talking about something called partial molar quantities. All right? And so, consistent with what we've said for the chemical potential, which is a partial molar quantity, this just tells me how any thermodynamic function changes due to changing number of moles. Right? So if I had a gas mixture, I could say that the pressure depends on the number of moles in there. Right? So the change in the pressure due to changing number of moles would be the partial molar quantity. Okay? Right. And then I have to indicate a little bit about how we symbolize these things. All right? And so we're going to say that we've got this function y. So y is a generic thermodynamic function. That indicates that it's a partial molar quantity. That little j down there says it's for a component in a mixture, right? And that basically is equal to the change in that thermodynamic property due to a change in the number of moles of that component, holding T, P, and Nj, all right? The other component moles constant, all right? Well, it's a pretty abstract concept. We'll try to make it a little less so in an example in a minute. Right? We're also going to be introducing the Gibbs-Duhem equation. Right? So the things that we're doing now that are different than what we've done before is we've been mostly talking about single component systems. Right? So we're adding components. So from the Gibbs-Duhem equation, we're going to show that we have chemical potential 1 and chemical potential 2, where those are the chemical potentials of individual components of a mixture. All right? So we're going to see that in general, mu1 is not equal to mu2. Right? That's the one thing that we'll see. But the other thing that we'll see is that if I change the chemical potential of component 2, it's going to impact component 1. Right? And so that also tells me that if I know component 1 and I know its change, I'll be able to calculate the change in the second component. Right? So we'll say relates chemical potential component 1 and chemical potential component 2. Okay, they're not independent of each other. All right? And then we're going to be applying an ideal solution. How many people have heard of Raoult's law before? All right, a number of you. Did that show up in general chemistry, Chem 2? No? Just chemical engineering courses? All right, so for Raoult's law, I'm going to write it out at the beginning. All right? This is Pi. This is the equilibrium vapor pressure of component I. All right? And one would expect that it's going to be related to the equilibrium pressure of component I when it's pure. All right? And the very simplest relationship that you can get, let me write this down. So this is pure I. Okay? The very simplest relationship that I can assume is that there's a proportionality between these two. All right? And we choose the mole fraction, xi. Okay? Does that make sense? Okay? All right, so the way that you think about this is if your solution's 90% component 1, that means that the pressure above that solution due to component 1 is 0.9 times the pressure when it's pure. Okay? All right, section 1, we're going to talk about partial molar quantities. All right, so we're going to be talking about a mixture. So we have two components. If I don't say anything else about them except that I have a mixture, it can be solid, liquid, or vapor, we know that that Gibbs energy has a dependence on pressure and temperature. And now what we're adding is the number of moles of one of the components and the number of moles of the second component. Right? So knowing that the Gibbs energy depends on these allows me to write a total differential that says, what's the impact of changing the temperature on the Gibbs energy? What's the impact of changing pressure? What's the impact of changing number of moles of components 1 and 2? All right? So that becomes dG will be partial of G with respect to T, holding P, N1, N2 constant times dt, plus the partial of G with respect to P, holding T, N1, N2 constant times dP. Right? That's nothing new. We've seen that previously. Right? And now what we're adding in there is dG dN1. So this is the impact on the Gibbs energy by changing the number of moles of component 1, holding temperature, pressure, and N2 constant. And then the last variable that we need to worry about is the impact of the number of moles of component 2. Again, holding temperature, pressure, and N1 constant times dN2. Okay? All right, and we've played with these before. We know that dG dt and dG dP correspond to something else. What's dG dt? Minus S dt. And dG dP is on the board is the same as VdP. Right? That's only molar volume if it's a molar Gibbs energy. Okay? All right. And then last time we met, this was our definition of the chemical potential. So that becomes mu for component 1, dN1, plus mu component 2, dN2. Right? All right, so this gives us our change in the Gibbs energy due to changes in temperature, pressure, and number of moles of each of the components. If we choose to focus on changing the number of moles, we're going to say we're going to hold the temperature constant, we're going to hold the pressure constant, dt and dp are equal to 0, and then I'm left with the chemical potential times dN1 plus chemical potential for the second component, dN2. Okay? All right, and then if I want to take this and get from the differential form to the integrated form, I need to do an integration. All right? So I take this equation. This is integrated, page 389. All right. And the result of this integration is that G is given by the chemical potential of one of the components times the number of moles of that component plus the chemical potential of the other component times the number of moles of that second component, right? And so if we step back and think about this, this says if I want to know what the Gibbs energy of the system is, I take the chemical potential times its number of moles for each of the components, right? Now we can extend that same concept to any partial molar quantity. So what we can say is that Y is going to be given by the partial of Y with respect to n for component 1 times n1 plus the partial of y with respect to n2 times n2 t p n2 constant t p n1 constant. All right? And this partial derivative is what we've called or introduced previously as y bar for component 1, and this is y bar for component 2. Okay? So this is the partial molar quantity for component 1, partial molar quantity for component 2. Okay? All right, so again, that's fairly abstract. So I wanted to look at an example where we talk about this in terms of something that's a lot less abstract. Right? So we're going to talk about determining the volume of a solution that's made by combining ethanol and water. So we can say that our total volume is going to be given by the partial molar volume of H2O times the number of moles of H2O plus the partial molar volume of ethanol, ETOH, times the number of moles of ETOH. Right? And that will give me the volume of the final solution. Okay? All right, now in order for me to do that, I need to know what the partial molar quantities are. All right? So we're going to get that off of this graph. So in blue, we've got partial molar volumes of water, so that's this term, and we can clearly see that it's a function of the mole fraction. So we need to know what the mole fraction is. And then for ethanol, this black curve corresponds to the partial molar volume of ethanol, right? So the solution that we're making is 2 moles of water and 2 moles of ethanol. So XH2O is going to be equal to, help me out, 2 over 2 plus 2, or 0.5, and that's the same as X ethanol. Okay? All right, so now I can go to the graph and I say, all right, there's 0.5. Come on up. That gives me the partial molar volume for water. All right, so I can say this time the volume of our solution is going to be equal to the partial molar volume. I've carefully determined it to be 16.9 centimeters cubed per mole. I need to multiply that by the number of moles, 2 moles, right? And that's H2O's volume. We'll just say H2O's volume. All right? I need to do the same thing, but now for the ethanol, all right? So I continue along the 0.5 trajectory, and that comes out to be 57.3 centimeters cubed per mole, and again times 2 moles. Right? And that represents the volume of the ethanol. Right? When I calculate those out, I get 114.6 centimeters cubed for the volume of ethanol. And I get 33.8 centimeters cubed for the volume of H2O. Okay? All right, and then I sum them together, and I end up with, what do I end up with? 148 centimeters cubed. Okay? All right, so let's talk a little bit about what that compares with if we expected volumes to be additive. So if I have pure water, 2 moles of it occupy 36 milliliters, and 2 moles of pure ethanol, 117 milliliters. We can clearly see 33.8, 36 not the same, 117, 114 not the same. So when I sum these together, I get a larger volume than I get whenever I mix these two in actuality. All right? Okay? All right. So does that make sense? Okay? All right, so this is a direct application of a partial molar volume. Pretty reasonable to wrap your head around. Okay? All right, and then not to go into any great depth with this, but if you think about water, you know, water has the solid phase is very open because of the hydrogen bonding. Liquid water is also fairly not as dense as it would be without the hydrogen bonding that holds the molecules far apart. So when I mix this with ethanol, the ethanol disrupts that open cage system and makes the volume lower. Okay? All right, so we're going to talk about the Gibbs-Duhem equation. As we said at the outset, we're basically going to show that if I have a mixture, the chemical potentials of the two components are not the same in general. But if I know the chemical potential of one, I can determine the chemical potential of the other. So they're related. All right, so we're going to start with, we've previously stated that the Gibbs energy is given by the chemical potential times the number of moles for each of the components in the solution. And what I can do with that equation is I can differentiate it, right? And if we recognize these are products, so I need to use the product rule. So this says that first term will become the chemical potential for component 1 times dN1, change the number of moles of component 1. Using the product rule, the next one will be N1 times the change in the chemical potential of component 1. All right? I do that for the second term. Right? So that becomes chemical potential 2 dN2 plus N2 d chemical potential 2. Okay? Now, previously, we've shown that dG is the same as chemical potential dN1 for each of the chemical potentials. And what I can do is I can subtract this equation from this equation. All right? So let's look at the left side. That means I have dG minus dG. What's that going to go to? That's going to go 0. All right? And then we compare and we see, well, I've got the chemical potential times the differential of the number of moles for both of the components in both of these. All right? And that means those are going to disappear. So chemical potential 1, dN1, chemical potential 2, dN2, they go away, and that's going to be equal to N1 change in the chemical potential for component 1 plus N2 change in chemical potential for 2. Okay? And already we can see that if I change the number of moles, that's going to impact both of these chemical potentials. Okay? So that's one version of the Gibbs-Duhem equation. Now to make it a little bit more usable, I'm going to divide it by the total number of moles, N1 plus N2. And when I do that, this becomes 0 equals mole fraction of component 1, the change in the chemical potential for component 1, plus mole fraction for component 2, the change in the chemical potential for component 2. Okay? All right? And then what I can do at this point is I can say, well, what if I know D chemical potential 1? I know how that's changing. How does that impact chemical potential 2? Well, I can rearrange this and say, set them equal to each other. That's going to get me minus x1 D chemical potential 1 divided by chemical potential 2. Okay? All right? And if you think about it, this equation, the fact that we've derived it tells us that chemical potential 2 depends on chemical potential 1. All right? And in general, unless the mole fractions are equal to each other, the chemical potentials aren't equal to each other. Okay? Right? But in principle, if I know chemical potential 1 of my phases, I can determine it from my other phase. Okay? Or my other component. All right, so in 10.3, we're going to talk about an equilibrium situation at equilibrium for a mixture. We're going to show that the chemical potential, and this should make sense, but we're going to demonstrate it explicitly, that the chemical potential for one of the components is the same in all the phases that are at equilibrium at that temperature. All right? So, let's say we're talking about salt and water, and let's say it's at the freezing point for the salt, for that mixture. Right? What we're saying is that the chemical potential of the water in the solid state is the same as the chemical potential as the ice state. And the sodium chloride, the sodiums and the chlorides have the same chemical potential in the water phase as they have in the solid phase. Okay? Right? And that should make sense because if they weren't, we wouldn't be at equilibrium between those two phases, right? They would go, the water in the ice phase would move into the liquid or vice versa. Okay? So at equilibrium mixture, chemical potential for a component is the same in all phases. Again, at equilibrium. Okay? All right. And just to put, before we go into this a little bit further, let's just say what this is telling us. So if I exist on the solid gas coexistence curve, that's where sublimation is occurring, where we have an equilibrium between the solid and the vapor, that says the chemical potential of solid is the same as that of the vapor phase. If I'm on the melting line, right, melting point line, chemical potential of solution is the same as the chemical potential of the liquid. The solid and the liquid are the same. And for vaporization, liquid and the vapor, right? And if you step back and recognize this is fairly powerful, that says if I want to know what's going to happen in the vapor phase, I need to focus on the chemical potential. I don't care whether it's the liquid or the vapor phase. So I'm going to choose the one that's easy to calculate. Does that make sense? Okay. All right, so we're going to start by looking at a single component. We are saying that we have a Gibbs energy that's due to the Gibbs energy in phase A and in phase B, right? And if I have two components, there's going to be a Gibbs energy for one component for phase A and another component for phase A, right? So we're just interested in one component. So we can differentiate, and then what we can say is that, well, if we're focusing on one of the components, dG will be given by the change in the Gibbs energy for phase A due to the change in the number of particles for component I, or no, I better do J because that's what it says I'm doing, in phase A, holding temperature and pressure and Ni constant times the change in the number of moles of component J into or out of phase A, right? All right, so that's the impact on phase A's Gibbs energy just from component J, all right? And then I do for the second phase, dG for phase B, due to a change in the number of moles, component J for phase B, holding temperature and pressure, and now number of moles of phase of component I constant, and then times D and B for component J. Okay? Now, because this is component J, going from one phase to the other, there's a relationship between moving into phase A and out of phase B, right? So D and B for component J is going to be the same as the change in the number of moles of that component from phase A. But what else do I need to make this true statement? I need a negative sign, right? Thank you. All right? And then we recognize that this dG, dN, well, that's our chemical potential, right? So this is the same as saying dG equals chemical potential phase A component J times dNJ phase A, right? So those are multiplied by each other. And now this will be chemical potential for phase B for that component, right? But because I have dNB in there, I have to add in my subtraction, chemical potential phase B component J times the change, right? So I've replaced this with the chemical potential. I've replaced dNB with minus dNA, and that gets to be minus the chemical potential, right? If we say that we're at equilibrium, we know dG has to be equal to 0, all right? And if dG has to be equal to 0, that tells me that the chemical potential for phase A and phase B for that component are equal to each other, okay? All right? And again, so what that tells us is that if I'm interested in knowing the chemical potential of a component, if it's at equilibrium between two phases, I don't care which phase it is, okay? We're going to choose the one that makes it easiest for us, okay? All right. So this is where your textbook bugs me a little bit in some of the ways it chooses its nomenclature. So this is the chemical potential for component I in the solution phase. So that's in a liquid solution. And this is a solution in the vapor phase, right? And because they're at equilibrium, we know they're equal to each other, okay? All right, and this is where I have a little sidebar. Right? So, and this was alluded to at the beginning. The change in the chemical potential with respect to the pressure is the same as the molar volume. All right? And so if I assume this is an ideal gas, I can say that's RT over P. I can rearrange this. That becomes the change in the chemical potential is equal to RT over P dP. And then I can integrate that. And the result of that integral gets me the chemical potential at some temperature and pressure relative to the chemical potential at 1 bar is this integral, right? And we've seen before that's the natural log of P, okay? Right? And that's where we get this equation, which is why I've written these both together here, right? So this is just a corollary from the Gibbs energy extending that same derivation now to chemical potentials, okay? So putting that all together, what we can say is that, whoops, let me make sure I'm on the right page here. So the chemical potential for component I at 1 bar at some temperature plus RT ln P for component I reference to 1 bar. Okay? All right, so to save a little bit of writing time from here on out, we recognize that this thing is a function of temperature. All right? So I'm going to just leave it out and just write chemical potential. Next up, I can say, well, what if our component is 100% pure? Then what we can say is that the chemical potential star is going to be equal to the chemical potential of that component at that temperature at 1 bar plus RT ln partial pressure, or the vapor pressure for the pure solvent over 1 bar. Okay? All right, so I've just rewritten the same equation. This is as a component, this is as pure, right? And then I can subtract one from the other, right? And when I do that, what we see is going to happen is that this chemical potential at 1 bar at that temperature is going to go away, all right? And then I'm going to have the chemical potential of my component in the mixture minus the chemical potential when it's pure. Right? And that's going to be equal to, well, now we look at this and we say, well, we've got RT, natural log. I'm taking this minus this. That means I can include this in here. Okay? And because I'm subtracting it, it's taking the reciprocal. Right? And so that becomes equal to RT ln Pi over Pi star. Okay? All right. And then we can rearrange it and say that my chemical potential for the liquid or the vapor phase of our component is given by chemical potential for when that substance is pure plus RT ln Pi over Pi star. Right? And this is a fairly important equation whenever you're thinking about energetics of solutions and what's going to happen with solutions. Okay? All right, so the other thing we just want to make sure is that this collapses where we expect it to collapse as our mixture becomes pure. So as the pressure becomes the same as the pure substance, that really tells me that Xi is approaching 1, all right? So I'm going in the limit of pure component 1. And that also tells me that Pi over Pi star is approaching the value of 1, all right? And the natural log of 1 is 0. And so that says that our chemical potential is approaching the chemical potential of the pure liquid. Okay? All right, now you might step back and say, you know, we talked about putting fugacities into these equations. Why aren't we doing it here? Well, it adds a level of complexity. But the thing that we know is that vapor pressures are usually not that high. And we know that most gases behave ideally at low pressures. Right? So for our discussions, pressure is fine to use. Okay? All right, so we're going to talk about ideal solutions. And what defines an ideal solution is that it obeys Raoult's law for all compositions. All right, and then just a reminder of Raoult's law. It says that the pressure of our component over a solution, right? Let me just put a little box here. So we have a closed container. I have a solution here. I put dots and X's to indicate that I have more than one component. We let this mixture reach equilibrium, all right? The pressure of one of the components is going to be given by the mole fraction of that component times the vapor pressure if I only had that component in here, okay? All right, and again, let's just make sure that we define a few things here. So PI, equilibrium. P vapor over mixture. This is equilibrium P vapor for pure. And this is the mole fraction. All right, let's write down here a graph that we're going to build on in the future. I'm going to have x1 on this lower axis. So my minimum value of a mole fraction can be 0. What's my maximum value? It's going to be 1, all right? When I have 1, I expect that vapor pressure to be P star for component 1. And whenever I have nothing there, the vapor pressure for component 1 is 0. And Raoult's law says we have a linear relationship between those 2 points, right? So vapor pressure in a liquid mixture is a linear function of the mole fraction with slope equal to P1 star. Okay? All right, and that's a reasonably good place for us to stop. We'll pick up there next time. I left you out 1 minute early. You can all say thanks. Actually, I just looked at my midterm evaluations, and I did all right, except for handwriting.
You've been working on it?
Does it look like I have? It varies from day to day. All right, have a good one. Please remember to put your name and email address on the pads of paper that I've floated around the room. Give you credit for being here, except Tommy. It's too late.